17th lecture, and we are going to continue our high frequency response of small signal amplifiers. If you recall, the equivalent circuit of a common emitter amplifier at high frequencies was drawn yesterday like this: Vs, Rs, you ignored Rx, small rx, so you had R pi, C pi, and this voltage is V pi. Then you have a C mu, a GM V pi, finally an R0, then C0 and RC and RL. This is V0. RB we have ignored, not RB. Oh, there is an RB. Oh yes, of course. This is here. Capital R, capital B. Yes. Any other omission? Tell me. Rx we have ignored. Rx tends to 0. That's what you assumed. And we simplified Rb and R pi. These two parallel combination we said capital R pi, and the parallel combination of R0, Rc and RL. These three we called it RL prime. In addition, we had shown that this cross connection or the bridge capacitance C mu could be taken care of approximately by including a capacitance here at the input C pi plus C mu 1 plus GM RL prime. C mu approximately reflects to the input side as this capacitance, and this is due to the so called Miller effect. And we had called this total capacitance C pi plus C mu 1 plus GM RL prime as C subscript capital T, and C mu reflects on the output side by adding a capacitor to C0 plus C mu. This is an approximate Miller equivalent circuit. If I draw it a little more neatly, yes, okay. Now if I draw it a little more neatly, it shall look like this: Vs, Rs, R pi, Ct, this is V pi, and then you have no more bridging, GM V pi in parallel with the resistance RL prime and the capacitance C0 plus C mu V0. I would like to remind you that this simplification of C0 plus C mu on the output side was obtained by ignoring a frequency omega 3 which was equal to Gm by C mu. We saw that at frequencies around omega 2, which is 1 by RL prime C0 plus C mu, at around these frequencies the effect of omega 3 is negligible, and therefore omega 2 was the cutoff frequency of this output circuit. Okay, and we had found out that A sub V was simply equal to AVO, which was, what was AVO? Yes, what is the value? Minus GM RL prime. This is the AV is the voltage gain between V0 and V pi, which is the same as Vi. okay, divided by 1 plus j omega by omega 2, and this was an approximate value under the condition that omega 3 is much greater than omega 2. Agree? This is just to refresh your memory how this was obtained. Now, as far as the input circuit is concerned, if I call this combination as Zi, combination of R pi and Ct, then obviously Zi is equal to R pi divided by 1 plus j omega R pi Ct. Agreed? Therefore, AVS, which will be the product of AV and V pi divided by Vs, okay, would be Zi divided by Rs plus Zi. Agreed? This is AVS. AVS is the gain between V0 and the actual source voltage. Zi, as you can see, is also the input impedance of the circuit. This is what the source with its internal resistance sees when it looks into this circuit. Zi, that is why this subscript I is for input impedance, no longer Ri, it is Zi. Okay. Now, if I calculate this, AVS would be equal to AV0 over 1 plus j omega by omega 2, and then Zi divided by Rs plus Zi. This would obviously be R pi divided by R pi plus Rs multiplied by 1 plus j omega R pi Ct. Agreed? I have simplified. I have struck off the denominator of Zi. Okay. This I can write as AV0 divided by 1 plus j omega by omega 2 multiplied by, let me write this as R pi divided by R pi plus Rs. Then in the denominator, R pi divided by R pi plus Rs. So in the denominator, what you will get is 1 plus j omega Ct R pi Rs divided by R pi plus Rs, which is the parallel combination of R pi and Rs. Is that okay? Rs times R pi, and I am dividing by Rs plus R pi. I have omitted one algebraic step. Okay. This I can write as AVS0, that is AVS at midband, which means that you put omega tends to 0, so this term disappears, this term disappears. All that you are left with is AV0 multiplied by R pi plus Rs. So AVS0 is the product of, let me write it down, AVS0 is equal to minus GMRL prime, that is AV0, multiplied by R pi divided by R pi plus Rs. That's it. Okay, and divided by 1 plus j omega by omega 2 multiplied by 1 plus j omega by omega 1. We define a new frequency omega 1, which is the reciprocal of Ct multiplied by R pi parallel Rs. So omega 1 is defined as 1 over Ct R pi parallel Rs. Okay. Let me clear this expression. Write it again. A sub Vs, a function of j omega, is equal to AVS0 divided by 1 plus j omega by omega 2 multiplied by 1 plus j omega by omega 1. Actually we should have a 1 plus j omega by omega 3 also in the numerator, but omega 3 we have ignored because omega 3 is much greater than omega 2. Now we shall show, okay, you see that there are 3 such factors, 1 plus j omega by some constant, okay, or 1 minus j, actually in the numerator it was 1 minus j omega by omega 3, isn't that right? In the numerator, if you recall, gm minus j omega c mu, so it was 1 minus j omega c mu by gm, there was a minus sign there, but these 3 factors correspond to 3 capacitances. Because there are 3 capacitances in the circuit, normally you expect that there shall be 3 such factors, 1 plus j omega by omega 1, j omega by omega 2, either plus or minus. It can occur in the numerator, it can occur in the denominator, alright. 3 capacitors, so 3 terms like this. Do you also recall poles and zeros? Okay, naturally this function has 2 poles, okay, at s equal to j omega is to be replaced by s, so s equal to minus omega 2 and s equal to minus omega 1, and if I had included the other term, the term that I had ignored, 1 minus j omega by omega 3, there was a term like this. You see that the pole 0 diagram is like this, sigma j omega, pole 0 diagram. One is a 0 at s equal to omega 3, okay, due to this factor. There is a pole at s equal to minus omega 2, somewhere here a pole is denoted by a cross, and a pole at minus omega 1. I have intentionally shown omega 1 closer to the origin than omega 2. We shall indeed show that omega 2 is usually much greater than omega 1. No, j omega is to be replaced by s. If I find this as a function of small s, the Laplace variable, AVS of small s would be 1 minus s by omega 3 divided by 1 plus s by omega 2, 1 plus s by omega 1. So the poles are at s equal to minus omega 1, minus omega 2, and the 0 will be at s equal to minus omega 3. I am sorry, s equal to plus omega 3. Okay. I have shown omega 2 as far away from the imaginary axis, from the origin, than omega 1, and this is in general true. Omega 3, unfortunately I have shown it here, but omega 3 should have been somewhere here. Okay. Omega 3 is much larger than omega 2. That means this distance would be much larger than this distance. Okay. So omega 3 is much larger compared to omega 2, and omega 2 is much larger compared to omega 1. These are the 3 relative values. We shall take an example to show that these are approximately valid. But you see, we have ignored this. Now if omega 2 is much larger compared to omega 1, then naturally omega 1 is the critical frequency which will determine the frequency response of the amplifier. In other words, if this can also be ignored at frequencies around omega 1, then naturally this is again a low pass filter, first order low pass filter, that is the effects of C0 plus C mu, okay, the effect of C mu determines omega 3, they are all swamped by the effect of CT. C pi alone cannot do it. C pi is comparable, C pi is of the order of 10 puff, C0 could be 5 puff, okay, one is double the other, but CT swamps everything. CT is C pi plus Cm, the Miller capacitance, and it is the Miller capacitance which swarms everything else. Miller capacitance is C mu, although a small quantity, it gets magnified by 1 plus Gm RL prime, the mid-band gain. Okay. So, our approximate 3 dB cutoff frequency, high frequency 3 dB cutoff would be omega 1, which is 1 over what is it, R pi parallel Rs times Ct, okay, omega 1. Now, let us take an example. For the example that we have been considering, R pi is Rb parallel R pi. What was Rb? 220K and 220K, so it is 110K. Parallel R pi was 2.6K and this is equal to 2.54K. So, omega 1 is equal to 1 over 2.54K parallel Rs is, what was Rs? 600 ohms, that is what we took Rs. So, 0.6K, okay, multiplied by now Ct. Ct is C pi 10 puff plus C mu was 2 puff multiplied by 1 plus Gm RL prime, which was calculated earlier as 57.7. We did calculate this, so many puffs, and this works out to 1.62 multiplied by 10 to the 7 radians per second. Recall that omega 2 was calculated as 9.7 times 10 to the 7 radians per second. Now, this value obviously is not much larger than 1.62, it is about 6 times. Okay. Are we justified in ignoring omega 2 when omega 2 is only 6 times? There is a justification. I told you that in electronics much greater than means a factor of 10. This is not even 10, this is 6. How come we can justify ignoring this? The justification is as follows: square, that's right. You see, what happens is, if I write AV S as equal to AV0, the magnitude divided by square root of 1 plus omega square by omega 2 squared multiplied by 1 plus omega squared divided by omega 1 squared. Alright. Now, this can be written as AV0 square root of 1 plus omega square 1 by omega 2 squared plus 1 by omega 1 squared plus omega to the 4th divided by omega 1 squared omega 2 squared. Okay. If omega by omega 1 is of the order of unity, okay, if omega by omega 1 is of the order of unity, then this term can be ignored. This term will be much smaller than this term, and in this term you see the relative values are of omega 1 squared and omega 2 squared, not omega 1 and omega 2 by themselves. So, all that we need is not omega 2 much greater than omega 1, but omega 2 squared much greater than omega 1 squared, right? And in this case it is, the ratio is 36, which is much greater than 10.
So, could you please repeat the justification for the ignoring the last term?
Ignoring the last term, okay. Suppose omega is approximately the same as omega 1, then omega squared by omega 1 squared is 1, and omega squared by omega 2 squared would be 1 over 36, which can be ignored.
But this is a particular case in which omega is of the range of omega 1.
No, this is the range that we are interested in. Let me tell you why. What happens is the falls like this, and what I want is this is AV0, AVS0. Let's not make a mistake. This is AVS0, and what we want is the frequency, this frequency at which the magnitude is AVS0 divided by root 2. Now at about this frequency, the effect of omega 2 is negligible. This is what I want to show. So I am finding for frequencies near this frequency, which will be obviously close to omega 1. Alright. Therefore in this particular case, as in other cases to come, omega 1 squared, as long as it is much less than omega 2 squared, as long as it is 1 decade below omega 2 squared, you understand, 1 decade below means ratio of 10, we are perfectly in shape, we are perfectly in business, which means that omega 1 and omega 2 need to differ only by a factor of 3.2. Agreed? The square of which is approximately 10. Okay. So this simplification is a great simplification, and one has to use this in engineering designs. Now it is also of interest now to look back and see what approximation does this affect, what kind of error does this introduce. If you recall, our exact equivalent circuit was RS, let's draw this again, R pi CT okay, R pi CT, then you have a C mu. Oh, I am sorry, exact equivalent circuit, C pi. Okay, I want the exact analysis. I want to find out how much error does it introduce. Get an idea. Okay, C mu, then GMV pi, then C0 and RL prime. This is our exact equivalent circuit before we took Miller effect into account. All right. Now to analyze this, what one can do is to write two node equations. That's all that is required. One is in terms of V pi, this voltage is V pi, and the other node voltage is V0. So you have to write two node equations and solve for V0 by Vs. If you do that and simplify, I am skipping this step.
Sir, could you just re-explain the node equation will write?
Re-explain what?
The node equation will be right.
The node equation. You see, there are two. Vs is known. I want to find out V0. Okay. Now Vs and V0 are not directly connected. They are connected through another node V pi, another node whose voltage is V pi. Therefore I have to write two node equations. Well, let me write this equation. Vs minus V pi multiplied by Gs. Okay, this is the current that comes in. This would be equal to V pi G pi plus J omega C pi. This is the current that goes into R pi and C pi, plus the current that goes into C mu. It would be V pi minus V0 multiplied by J omega C mu. Agreed? This is the first node equation. The second node equation is V pi minus V0 J omega C mu. It is this current. That would be equal to Gm V pi plus V0 GL prime plus J omega C0. That's it. These are the two node equations, and all that you have to do now is to eliminate V pi. So take V pi from one equation and substitute into the other. The expression that you get now, what kind of expression do you expect the degree of the numerator and the degree of the denominator. What would be the degree of the numerator? 1, because I had only 1 0. The degree of the denominator would be 2. So I shall have omega squared term also. And the exact expression is this. Please do write this down. Minus GMRL prime, this is AV0, as in the approximate expression, multiplied by R pi divided by R pi plus RS. This takes account of the midband gain at the input. So this whole quantity is AVS0 as in the earlier case. Then we have 1 minus, as we had found out, j omega divided by GM by C mu. This was omega 3, okay, and divided by, now here comes the difference, 1 plus j omega divided by, what I get here is R pi parallel RS times CT. Well, it does not stop here. In the approximate expression we had simply j omega by omega 1, and omega 1, I beg your pardon, I have made a mistake. Okay, now it's okay. Alright, I have left a gap intentionally. I will tell you why the gap is. You see, in the approximate expression it is simply this, and this inverse, no, this quantity was taken as omega 1. No, omega 2 is different. Omega 2 comes as 1 by RL prime C0 plus C mu. This inverse was taken as omega 1. In the exact expression there is in addition a term which is C0 plus C mu RL prime. That is the term which contributes to omega 2 also occurs here, and it's quite understandable because even in the approximate expression the coefficient of j omega should have been 1 by omega 1 plus 1 by omega 2, approximate expression. In the exact expression the two add to each other. Okay, so this we shall call omega 1 prime. It's not quite omega 1, it's omega 1 modified omega 1, and then you have an omega squared term, and this squared term is like this, minus omega squared, it is still in the denominator, RL prime R pi parallel RS multiplied by C pi C naught plus C naught C mu plus C mu C pi. This is the expression. Okay, normally it should have been omega squared divided by omega 1 squared multiplied by omega 2 squared in the approximate expression.
This is the denominator?
This is all in the denominator. Okay, this is all in the denominator. And what we have done is we have ignored this, which can be ignored in an actual circuit, and instead of omega 1 prime equal to this we have ignored this term. Okay, and the condition, well, before we find out the condition under which this can be ignored, let us take the exact expression and substitute the numerical values and see what sort of approximation you get. These have been calculated, and the values of AVS have been found out at the magnitude, not the magnitude, the total expression. Obviously you have to feed it into a computer, I mean hand calculation would be too large, at various values of omega. Now will you give me the value of omega 1? What did we calculate? 1.62 times 10 to the 7. And what was omega 2? 9.7 times 10 to the 7. Okay. So what we did was calculate at omega equal to 10 to the 7 just before omega 1, at 2 times 10 to the 7 at 3 frequencies we calculate, that is immediately after omega 1, around omega 1, and then and then at a frequency nearly equal to omega 2. We calculated at 10 to the 8. 3 frequencies we calculated, and we calculated the approximate value, that is by using the Miller model, and the exact value, that is by using this horrible looking expression. Okay. Alright, the values that we get are very illuminating. The approximate value is 39.7 magnitude, and the angle, instead of 180 degree, at mid band the angle is 180 degree. It now becomes less than 180, it becomes 148 degrees. It's a complex expression, find out its magnitude and its phase. Obviously you have to feed it into a computer. Okay, and the exact values come 37.9, angle 144 degree. You can calculate the percentage error, but you see they are reasonably good approximations. Okay, at 2 times 10 to the 7, do you expect the gain to be more than 39.7 or less than 39? Less. And the value is 29.4, 129 degrees, and the exact is 26.8. You see the error is increasing. Why? Because you are going closer to omega 2. If we had calculated a 10 to the 6, the error would have been much less. Alright. So 26.8, and the angle is 124 degree. And far away, that is nearly at omega 2, the gain is still less, 7.47, the angle is 109 degree, the exact value is 6.48, angle 103 degree. The angle does not change substantially. Okay, between the exact and the approximate, you see this is 4 degree, this is 5 degree, this is 6 degree. The angle doesn't change substantially, and 4 degrees in what? 144 degrees. So the percentage error is much less. It is in the magnitude. Now one argues that we won't obviously use the amplifier with a gain of 7.47 when the mid band gain is, what was the mid band gain? AVS 0?
57.7.
No, 57 point, okay, minus 57.7 multiplied by R pi. What was R pi? 2.54 divided by 2.54 plus 0.6, and this value, no, I have not calculated. Anyway, this value, as you see, it's approximately 56. Okay, 2.54 divided by 3.14. Okay, it's greater than 50. Obviously, we will not use the amplifier when the gain becomes 7.47. We will go approximately up to 2 times 10 to the 7, not more than that. So the 3 dB cutoff being taken as omega 1 is justified, even by exact analysis. Yes, pardon me?
Minus 46.7.
Minus 46.7. Okay. So if at mid band we require 46.7, obviously we will not go beyond, let's say, 30 on this side. On the lower side also there will be a decrease of gain, which we shall calculate later. Yes, your question.
If the frequency is higher, then we should have a larger error between exact and approximate results.
That's right.
But in this case, we see that for 2 into 10 to the power 7 as the frequency, the error is more as compared to 10 to the power 8.
Okay, that's a good point. Percentage error. That's what counts, not the absolute error. Okay, you have answered the question. This is like a self-interview. You know what is a self-interview? No, after the class. Okay, now as far as an FET amplifier is concerned, the analysis is exactly similar. So I shall only recall the steps in the analysis and give you the results. The algebra I will not carry out. The circuit let's draw it. There is no harm in repetition. The circuit is VDD R sub D. You have a drain, a source. The source is bypassed. A common source amplifier with a C sigma. There is a capacitor C2 which goes to RL. The voltage is V0 and the biasing is done by two resistors R1 and R2, the sole purpose being to establish a voltage at the gate. Okay, I have shown an N channel JFET. The sole purpose of R1 and R2 is not to feed a current like a BJT. This must be understood. BJT requires a base drive, not voltage but a current, because otherwise I sub C shall be 0. I sub C is approximately beta times T. But here this is not the case. Here all you want to establish a voltage is a voltage at the gate and a voltage at the source such that VGS is negative or positive? Negative in an N channel JFET. Okay. And then you have the capacitor C1, RS and VS. Okay, this is the circuit, and the equivalent circuit would be VS. AC equivalent circuit would be VS. C1 is taken as a short, so RS, it goes straight to R sub G, which is a parallel combination of R1 and R2, and then you have a capacitance of value C G S. Okay, then from the gate to the drain you have a capacitor C G D, and the voltage here is VGS. The current source here would be GM times VGS, where GM now has to be calculated as, if I recall, GM is minus twice IDSS divided by VP multiplied by 1 minus capital VGS divided by VP. Wonderful. You have to calculate this. Okay. Then this goes to ground. What do we have here? A dynamic RD, dynamic drain resistance, and we have the parallel combination of RD and RL. This voltage is V0. As usual, we effect simplification by combining this into RL prime. That's all. There is no R pi here. Okay, so if I now take Miller effect into account, then CGD, I have made a mistake and I am waiting for the correction.
There is no minus.
C0, there is a capacitor here, C0, and if I want to analyze this by Miller effect, that is avoid this bridge which creates complications, we have to write two node equations. If I want to avoid this, then all I have to do is add 2 CGS as CGD multiplied by 1 plus GMRL prime, and 2 C0 I have to add CGD. Okay, this is the Miller effect equivalent circuit. You want me to draw this more neatly or?
Yes, sir. Yes, sir.
Okay, whatever you want. VS RS, why don't we draw this as a ZG? What is ZG? It is RG divided by 1 plus j omega RG multiplied by CT. Once again, this capacitance, total capacitance, I shall denote this by CT, is equal to CGS plus CGD 1 plus GMRL prime. This is VGS, and then I have a GM VGS and a C0 plus CGD and an RL prime. This is V0. Naturally, since we have converted 3 capacitor circuit into 2 capacitor one, that 0 in the numerator we have ignored. Okay, and there would be 2 poles now, one due to Z sub G and the other due to C0 plus CGD, as in the BJT case. And as usual, the same relationship would be true. That is, if we define, let me do it in this figure itself, if we define omega 2 as 1 over RL prime C0 plus CGD, okay, and omega 1 as what? 1 over Rg multiplied by Rg parallel Rs, do not forget this, multiplied by Ct. If we define these two cutoff frequencies, then omega 2 would be much greater. No, that may not happen. What should happen? Omega 2 squared, let me write it in a brighter color. Omega 2 squared will be much greater than omega 1 squared. So that our gain expression AVS of j omega would be given by AVS 0 approximately divided by 1 plus j omega by omega 1, where AVS 0, tell me what the value is, minus GM RL prime multiplied by Rg divided by Rg plus Rs. Okay, and omega 1 is given by 1 over Rg parallel Rs multiplied by Ct under the usual approximations. Okay, since we have done the BJT circuit in details, we didn't have to do FET in details. I avoided all the algebraic steps. Once again, it is of interest to find out what kind of error. Error may not be the same as in the BJT, because the values of the resistances are quite different. They are of different magnitudes. So one has to calculate the error. And if you want to calculate the error, then you have to analyze the exact circuit with a 2-node analysis. 2-node equations have to be written and have to be solved. Let's see, if I have the expression, I shall give you the exact expression. But let's quickly look at one example. In this example, we assume that Rs is equal to 1K. Rs was 600 ohms in the BJT. Why have we increased it? Because FET can take higher values of source resistance. Why? Because FET input impedance is very high. Very good. R sub D is 5K. RL, it can take larger load also, 10K. R sigma is 2K. R1 and R2 both are 100K. CGS is 3 puffs, CGD is 2 puff, GM calculated from I sub D is 10 millimole typical value, and R sub D is 20K. Suppose GM was not given, suppose this was not given, could you calculate GM from this data? What? So what do you need? ID. Who is going to give you ID? IDSS. And what else? VDD would have been needed, isn't that right? We have not given that because all the parameters are given. Agreed? VP also, that is correct. If GM was not given, then you ask for 3 more data. VDD, why is VDD needed? To calculate VGS, come to the point. VDD is needed to calculate VG. Alright, not VGS, VG. VS will be calculated from ID times R sigma. So Vg minus Vs, that you have to substitute in the expression for ID and solve a quadratic. There you have to exercise your intelligence to reject one of the values. One value will be admissible, the other shall not be. Okay. Now if this is so, then AVS0 is given by minus GM RL prime RG divided by RG plus RS. Substitute these values and it calculates out to minus 28.6 multiplied by 50 divided by 51. Why did I calculate this separately? Pardon me? Why did I calculate this separately? This I will require for the Miller capacitance. Miller capacitance is CGD multiplied by 1 plus. Now if you put this in a calculator and calculate, you will soon discover that you will have to go back and calculate the GMRL prime also. So it's better to calculate this in 2 steps, and this becomes minus 28 approximately, and omega 1, the frequency omega 1 is 1 over RS parallel RG, and the capacitance is CGS plus CGD 1 plus GM RL prime, and that calculates out to, after a bit of calculation, to 16.4 times 10 to the 6 RPS. It is of interest to know whether this dominates or not. That is, it is of interest to calculate omega 2 also. Omega 2 is given by 1 over RL prime, then C naught plus C GD. It has not been given. So what is given is CGD. How much was given? 2 puff. C0 will be comparable to CGD. So even if this capacitance C0 plus CGD, let's assume it to be 3 puff. So even if this is 5 puff, even if C0 plus CGD is 5 puff, well, if it is 5 puff, then this calculates out to 66.7 multiplied by 10 to the 6 radians per second. Alright, 66.6 10 to the 6 radians per second, which is only 4 times approximately, but square is 16 times, so the approximation is justified. I will strongly encourage you to find out the exact expression also. To find out the exact analysis, I have the expression. Yes.
So how do you assume C0?
How do I assume C0? C0 normally is the stray capacitance, and it is of the order of a few parts. You can take slightly higher, so long as omega 2 squared is 10 times. We have kept a margin here, right? So long as omega 2 squared is 10 times, it is okay. C0 can also be measured. In the actual wiring, you can measure, and you can reduce C0 by careful wiring. Okay? Right. Any other question? The exact expression for V0 by Vs by making a 2-node analysis is the following. Write it down and try to verify that it is indeed so. RG plus RS then you have 1 minus exactly like the BJT j omega divided by Gm over CGD. This is that omega 3 divided by 1 plus j omega by omega 1 prime, not omega 1, minus omega squared RL prime RS parallel RG times CGS CGD plus CGS C0 plus CGD C0. This is the exact expression. I do have some calculations regarding exact values, but I think we can skip that. Omega 1 prime, the only difference is RS parallel RG times CGS plus the Miller capacitance, that is CGD 1 plus GM RL prime. In addition, we have a term. Can you guess what this term is? Exactly like the previous case, it is RL prime C0 plus CGD. That's it. And usually this term is negligible. This term is negligible compared to the previous one. Well, sure. The condition under which this term will be negligible compared to this is that CGD plus C0 must be much small compared to GM CGD multiplied by RS parallel RG. Is that point clear? No. Okay. I want to ignore this compared to this. Now you know GM RL prime is much larger compared to 1. So you can ignore this. And you know the Miller capacitance swamps the total.
Where does this bracket? Where the brackets are closed? Square bracket.
It must close here. Where else can it close? It must close here. Okay. We can ignore 1 and then CGD GM RL prime will swamp CGS. So we can ignore CGS. What I want is that this term should be small compared to RS parallel RG multiplied by CGD multiplied by GM RL prime. You see, what was the purpose of this simplification? To cross out RL prime. We are finding out an inequality. So omega 1 prime, to make a profound statement, omega 1 prime is approximately equal to omega 1 if RS parallel RG multiplied by CGD GM is much greater compared to CGD plus CZ. Okay, this is the condition. No RL prime we have, there is an RL prime here, there is an RL prime here, so we have crossed that out. We wanted to find out independent of RL prime. You see, all that it involves is the internal parameters of the transistor, the JFET, the external resistors RS, R1 and R2 and the stray capacitance C0. Okay. Under this condition omega 1 prime would be equal to omega 1. I have some calculations. Assuming C0 as 1 puff, for the same example as we had taken earlier, assuming C0 as 1 puff, we get omega 3, which is GM by CGD, is 5 times 10 to the 9 RPS. AVS0 we have already calculated. Omega 1 prime calculates out to 14.4 times 10 to the 6 RPS. What was the value? What was omega 1? 16.4 times 10 to the 6. So it's not too bad. Ignoring the second term, instead of 14.4 we get 16.4. That's not too bad. Okay. In any case, in an actual circuit you shall have to make adjustments. So one can afford to become a bit rough with circuit calculations, electronic circuits in particular, because you will have to make fine adjustments and so on. And this is a good point to stop. Next time we are going to talk about low frequency response.